Hi, welcome to the video lecture for the correlation and regression section of the course. And this is actually our last video lecture for this semester. We're going to start by reviewing correlation, which we talked about earlier on in the course. And so it might be a good idea for you to go back and actually watch that lecture again. But here are the highlights. So we've got a sample correlation coefficient and a population correlation coefficient. The sample correlation is R, capital R, lowercase r, it doesn't matter. The population correlation is the Greek letter rho. R is our best estimate for rho, so R is going to be our point estimate of rho. Correlation measures the strength and the direction of the linear relationship between two quantitative variables. Correlation is measured on a scale from -1 to 1, where negative values mean that as one variable increases, the other one decreases. So if you're looking at a scatter plot, a negative correlation would be going down from left to right. And a positive correlation means that the two variables, if one of them increases, the other one does too. So if you're reading that left to right, that would be going up from left to right, a positive slope. So direction for the relationship is measured by whether it's negative or positive. The strength is by the magnitude of the correlation, how close it is to 1 or 0. And then we gave these rough guidelines, which is an absolute value of R less than 0.1 means there's no meaningful correlation. If R, whether negative or positive, is between 0.1 and 0.3, that's weak. 0.3 to 0.5 is moderate, and then more than 0.5 is considered strong. These are very rough guidelines, just like with any of the other effect sizes we've looked at. You always want to compare to the context, take the context into account, and compare to other similar studies in the field. So we said we've got the sample correlation and the population correlation. Well, we can use the sample correlation to try to make an inference about the population correlation. And we're going to do that by doing a hypothesis test. So with the correlation test, we can determine if there's a linear relationship between two quantitative variables. And so our hypotheses are, the null hypothesis is always that rho equals 0, which means that the population correlation is 0. And that would indicate that there is no linear relationship between the variables in the population. The alternative hypothesis that we're going to test is going to be rho differs from 0. We could test, we could do a one-tailed test, but we'll just do a two-tailed test. Because if rho differs from 0, either way, that means that there is a linear relationship between these variables. We'll get the p-value from either StatCrunch or SPSS. And then the effect size is the sample correlation coefficient, the R, the one that with these guidelines here, as you saw on the first slide. Okay, so let's do an example. So let's look at whether there's a relationship between somebody's ACT score and their end-of-year GPA after their first year of college. So the ACT scores are given as percentiles, and GPAs are on the standard 4-point scale. And as with most of this data, I just made it up, so I don't know if this reflects reality or not. So I've got this data over into StatCrunch, and everything we need is going to be under Stat. Go to Regression, Simple Linear. We'll pick ACT as our X variable, and we'll pick GPA as our Y variable. That's because here in a minute we're going to do regression where we're actually using one variable to predict the other one. In this case, we want to use ACT to predict how somebody performs their first year of college. All right, so here under hypothesis test, just leave that at not equal 0. And if you want to predict a value of y, we'll get to that in a minute. So just hit compute. And this gives us the output we need. So you're going to copy this and, as usual, paste it into your homework. So let's talk about what some of that output tells us. So down here, this p-value is the p-value on the correlation test. Ignore some of these labels here. Well, I shouldn't say completely ignore them. Let me point out here, this says analysis of variance table. So we've seen ANOVA before. And I'll just mention that ANOVA and correlation and regression are very closely related. And I don't want to get any deeper into that right now, but I realize this says ANOVA. That's okay. And correlation and regression are kind of all part of the same thing. So anyway, so all that is to say that this is our p-value that we're looking for. This also gives us the correlation coefficient, and it gives us a value for r squared, which we'll get to in just a minute. But for right now, these are the three things we need. We need the correlation coefficient, we need the r squared, and we need the p-value. So our hypotheses are going to be row equals 0 versus row not equals 0. The p-value comes from that output, circled here, the 0.8357. We'll reject h-naught if p-value is less than 0.05. And since our p-value is larger than that, we will fail to reject h-naught and say that there is not sufficient evidence to conclude that these two variables are linearly related. Our effect size, the correlation coefficient, is 0.0672 from the output, which means that there's really not any meaningful relationship either way between ACT score and GPA. That's such a weak correlation that there's really nothing to that. All right, so that's the correlation test. Let's talk about regression now. Regression is a way of using one variable to predict the other using a straight line. You probably saw back when you were in algebra, y equals mx plus b. That's what we have going on here too. We have y equals, they label it b0 plus b1x. The slope of the line is b1 and the y-intercept is b0. That's for the sample. If we wanted to do a population, we could describe that as beta naught plus beta 1x. That's not so important. But if you look at the StatCrunch output, it tells us that the equation of the line, back here, the equation of the line is GPA is 3.0498 plus 0.0038 times a person's ACT score. And I'll point out here that these values are also in this table. When we get to SPSS in a minute, SPSS won't give you this part up here, it'll just give you the table. So we would get that from saying the intercept is 3.0498 plus 0.0038 times whatever your variable is. And that's the equation. All right, so if we wanted to use that equation to make a prediction, all we'd have to do is plug in the value we want to predict for into the regression equation. So if we want to use predict the GPA of somebody whose ACT score was in the 80th percentile, we could just take 80 and plug it in. Although, I'll point out that with such a weak correlation, you probably wouldn't want to do too much prediction with this equation. You'd want to have a stronger correlation in order to run the prediction. So anyway, so if you plug in to this equation, make sure you do your order of operations correctly. Do your 0.0038 times 80, and then add 3.0498. That tells us that our predicted value is 3.3538. That's our prediction for somebody whose ACT score is in the 80th percentile. So I have to preach for just a minute that when you're using the regression equation for prediction, be very careful. You don't want to predict outside the range of the data you have. So in our data set, and I've changed this here, but in our data set, we have values, we have percentiles that go from, let's see, the lowest is 58, and the highest is 92. So we wouldn't want to use this data to predict for somebody who got the 20th percentile on their ACT score. Okay, so we have to be careful and predict only within the range of the data that we have, because we don't know that this equation, that the relationship is linear outside of that. Also, be aware that correlation does not imply causation unless the data is an experiment. And in this case, we do not have a true experiment. We can't assign people different ACT scores and then observe what their GPA is as a result. Okay, so that's the two things I need to preach about there. So we've talked about correlation already as a measure of effect size, but let me mention also the coefficient of determination. We saw this before with ANOVA, and it's the same one we're looking at now. It has the same interpretation, the same guidelines as before. The guidelines are 0.01, I'm sorry, for small, 0.09 for moderate, and 0.25 for large. This again is part of, well, let me say this. Let me say, you see that R is correlation and R squared is the coefficient of determination. That's not a coincidence. Actually, if you take the correlation coefficient and square it, you get the coefficient of determination. But the coefficient of determination has its own nice interpretation. The same one we saw before, where it tells you what percent of the variability in Y can be explained by X. So in this case, if we go back and look at our output, R squared was 0.0045. So that's less than 1%. If you change that to a percentage, move it 2 decimal places to the right, that's 0.45%. So that's a little bit less than 0.5% of the variability in GPA can be accounted for by ACT score. So this is a small effect. Let me say just a little bit more about that. What this tells us, if you've got a low R squared, it tells you that there's really other factors going on that you haven't been able to explain why people have different GPAs. So in this case, ACT does a terrible job of predicting. We'd love to be able to predict somebody's GPA with 100% accuracy. We're never going to be able to do that. But this is telling us that ACT, we're barking up the wrong tree. We're barking up the wrong tree because ACT, according to this data which I made up, can only account for about 0.5% of why people are different, of what makes people different on GPA. All right, so example 2. So age and risk-taking behavior. So we want to use age to predict somebody's risk score. So if you want to take just a minute and try to answer these questions. Pause the video. I'll keep going. So I type this data in, and again, we're going to stat, regression, simple linear, and we want to use age to predict the risk-taking behaviors. So age is X and risk is Y. And we'll leave everything else the same and hit compute. Alright, so this gave us everything we need. We'll copy and paste it over here. And this is our output. So on question 1, state and interpret the correlation coefficient. R here is negative 0.6861. That's going to be a strong negative correlation. So that tells us that there is a strong relationship between age and risk-taking. And it's negative, which means as age goes up, risk-taking goes down. Number 2, using alpha equals 0.01, tell us whether these two variables are linearly related. So our hypotheses, H0 is that there is no linear relationship between the two variables. The alternative is that there is a linear relationship. The p-value is 0.0285. That comes from down here. And since alpha in the problem was 0.01, we'll reject H0 if p-value is less than 0.01. And here it's not, so we would fail to reject H0 and say that there's not sufficient evidence to conclude a non-zero correlation in the population. Now if we used 0.05, we'd get a different result. If we used 0.05, we would say reject H0, there is sufficient evidence to conclude a non-zero correlation in the population. Alright, part 3 says state the regression equation. We've got our regression equation over here. We just have to copy it down. That's it. Predict the risk score of a person who's 40 years old. So we just take this equation, plug 40 into it, and that gives us the predicted score. State and interpret, and I want the size as well as the meaning on all of your coefficients of determination. So on this one, r squared is 0.4708. We get that from the output here. That's a large effect size because that's greater than 0.25. And that tells us that 47.08% of the variability in risk-taking score can be explained by a person's age. Okay, so there are other factors that would explain the other 50-some percent, 52.98% or something like that, of why somebody is as risky as they are. But age is almost half of it. All right, so that's another example. Now, let's go to SPSS. So I have the example for ACT and GPA in SPSS. And we've got a couple other variables here too. So if we want to get the correlation, we can go to, and we did this before, analyze, correlate, bivariate, and we just move our two variables over here. Click OK, and you'll copy and paste this over. Just right click, copy special, and pick image. And so we have here our correlation coefficient, which is R, 0.067. And underneath that, where it says sig two-tailed, that's the p-value on the correlation test. Okay? Now to do the regression, we go to Analyze, Regression, linear. Our dependent variable is GPA at the end of second semester, and our independent is percentile score on ACT. You don't have to do anything else here, just click OK. And it gives you several things. There's two parts of this that we really need. We need the model summary, because that's where we're going to get our R squared, and we need the part that says coefficients. So for the model summary, like I said, this is where we get our R squared. Ignore the adjusted R squared. That means something different. Completely ignore that. So R squared here is 0.005. That's what we got before. And then our these are our coefficients. And so the coefficients are listed here, but you still have to write them as a regression equation. So GPA equals 3.050 plus 0.004 times the percentile score on the ACT. All right, so that's the regression that we've run so far. Now I need to move on and talk briefly, just very briefly, about multiple regression. And we'll only do this part in SPSS. Regression is a very, very common tool used in just about any research field. But one thing that we like to do is use more than one variable as a predictor. So you can imagine if you're an admissions counselor at a college, you want to use all the admissions, all of the information available to you to try to predict how whether somebody's going to succeed at your school. So we've got somebody's end of year GPA, but we've got some other information that may be included on an admissions application. Let's try to use all of that to predict GPA. So to do that, we just have to go back to Analyze Regression Linear, and we'll just pick all of our variables and put them over here. So we've got percentile score on ACT already, so we'll just move all of the other variables over into our block of independent variables. We'll click OK. And again, what we need is our model summary and our coefficients. So if we do that, this time our R squared is 0.688. So that tells us that now we've accounted for 68.8% of the variability in college GPA. So that's much better. We've been able to really narrow down there, not necessarily why, but we've been able to predict it with a good amount of accuracy. So that's what the R squared is. And then for the regression equation, it's just going to be GPA equals the constant, which is 2.5, minus, because this sign is negative, minus 0.022 times somebody's percentile score on the ACT, plus 0.924 times their high school GPA, minus 0.009 times the number of honors courses they took, minus 0.134 times the number of sports or clubs they were in high school. And that all is listed here. All right, so that's it on correlation and regression, and let me know if you have any questions.